There is somebody on this app that we will not name that has epic bad takes about basically everything about math, physics, academia. All of them are bad takes, uninformed takes. But the one that I still think is the most hilariously wrong is that integrals are easy and the algebra, the basic college algebra of solving the integral is hard. And that is so fantastically wrong that it's just comical. Integrals are so hard that 100%, 100%, and this is a theorem, 100% of all functions do not have an elementary antiderivative. That means that if you were to pick a function at random from the reals to the reals, that function will not have an antiderivative that can be expressed in terms of elementary functions. Polynomials, rational functions, algebraic functions, trigonometric functions. There is no elementary antiderivative. So there is no method that works because they do not have one. So when we teach you calculus, we have to be extremely careful about what functions we pick for problems, because most of the functions out there, they would not be functions that you can integrate using the techniques we usually teach. So if integrals seem easy at times, it's because we picked very easy and very specific functions that one can solve using U substitution or integration by parts. And again, this is a theorem. It's a theorem of Liouville that tells you that if you pick an arbitrary set of functions that you call elementary and you form the space generated by all those functions under algebraic operations, then there are always functions whose antiderivatives are outside of this space of elementary functions. And in fact, the total space is of much larger dimension than your space of elementary functions. Therefore, the space of functions that have antiderivative outside of your elementary functions is 100% of the space compared to the ones you pick to be elementary. And in fact, this difficulty of solving arbitrary integrals is the very reason why in Calculus 2 you learn about infinite series and Taylor series, Maclaurin series, because that is one way that we have to be able to do integrals of arbitrary functions and at least numerically compute values of such integrals.